Next, we'll move on to problem 8. This is probably the most important problem from this set of notes, mainly just because it's a bunch of practice involving definite integrals. So I think the main thing that you'll need in order to feel comfortable with this stuff is just a bunch of practice problems. So if you want some extra practice, you can pause the video and try these problems first before we talk over them, just so that you can get some immediate feedback on some problems. But we'll get started on them. So in problem A, we're trying to integrate from 0 to 2 the function 4e to the x. So if you are not yet comfortable with the rules for antidifferentiation or indefinite integrals, then I would recommend just having that set of notes pulled up in front of you so that you can see which rules I'm using. I'll also use some u substitutions later on in this problem, but let's first look at this one. So I have a constant factor on the inside that I can pull out of the integral. So I can factor out that 4, and then this would just become the integral from 0 to 2 of e to the x dx. I know that the antiderivative of e to the x is e to the x. So this would be a 4 e to the x evaluated from 0 to 2. And it actually doesn't matter whether you include the 4 as part of the thing that needs to be evaluated or as some factor on the outside of it. So you'll get the same answer either way. I think I'm going to treat this, though, as a 4e to the x evaluated from 0 to 2. That would give me a 4e squared whenever I evaluate at the upper limit, and then I need to subtract the evaluation at the lower limit. So this would be a 4e squared minus 4e to the 0. That would be a 4e squared minus, remember that e to the 0 is 1, so that would be a 4 times 1. And notice that this is the same thing that we would get if we had taken from this stage, if we had just left the 4 on the outside and then done the evaluation on the inside of some parentheses. This would be a 4e squared minus e to the 0th power. That would be a 4e squared minus 1, and then when you distribute the 4, you'll get the same answer that I got over here. So these are equivalent. Okay, next we're looking at this integral in B, the integral from 1 to 5 of 2 over x dx. So again, if I want to, I can integrate after pulling out that factor of 2. So this would be the integral from 1 to 5 of 1 over x times a 2. And we remember that the integral of 1 over x is ln of x, so this would be an ln of x evaluated from 1 to 5. And I normally like to treat that constant as part of this expression that needs to be evaluated. So this would be a 2 ln 5 minus a 2 ln of 1, and that would be a 2 ln 5. ln of 1 is 0, because the exponent that you would put on an e to get a 1 would be 0. So this is just 2 ln 5. You can plug that into a calculator if you want a decimal approximation, but this is an exact answer. Okay, so for this one, we can start integrating if we want to. So this is the integral from -3 to -3 of this expression, x squared plus 4x plus 2. Now, as we get comfortable taking these antiderivatives, I'm going to start skipping steps. So rather than writing this as 3 separate integrals and then factoring out the individual constants like this 4, I'm going to start just computing the antiderivative right away. But if you need some additional scratch work, then feel free to pause the video and split up into multiple integrals and then check that you get the same answer. But I'm going to start just finding the antiderivative of all of this without splitting into 3 separate integrals. So if you integrate the first term, it would become an x cubed over 3. For the second term, we have a factor of 4 that's just going to stick around. And then when I integrate x, it will become an x squared over 2. And then for that last term, the antiderivative of 2 will be a 2x. So this is what we'll get as our antiderivative here, and then we should evaluate from -3 to 3. Sorry, -3 to -3. So if you want, you can clean up the antiderivative a little bit, but not a whole lot. a 4 divided by 2 would just be a 2, so this would be a 2x squared plus a 2x. And now we can plug in if we want to, so this is still evaluated from -3 to -3. If you plug those in, then you would get something like -3 cubed divided by 3 plus a 2 times a -3 squared plus a 2 times -3 minus exactly that expression. So we would just be taking that expression and then subtracting it from itself. I'm going to run out of room here, but that's all right. So it's this expression minus itself. Anytime you have something minus itself, you'll end up getting 0. So this will end up being 0. So 0 is the answer here. So I decided to go through this problem just so that you'd have one additional example involving antiderivatives here, but it's okay with me if you want to stop immediately at the beginning and say, well, if you integrate from -3 to -3, you won't accumulate any area because these integral bounds are the same. So because you have two of the same integral bounds here, this will end up being 0. And that was a rule that we talked about just a second ago. Up here, that's rule number 1, actually. If you integrate from a to a, you end up getting 0 area. So in this case, because the integral bounds matched, we're not going to get any area. Next, let's look at this one. So we're integrating from 4 to 25, 2 over root x dx. For problems like this one, unless you just have integrals of something like 1 over root x memorized, I would recommend going ahead and rewriting this as a power of x. So this would be a 2 times x to the -1/2 power, because the 1/2 represents the square root, and the negative tells us to take this reciprocal and put the x in the denominator. So this would be a 2x to the -1/2 power dx. Now we want to take the antiderivative of the integrand. So when I take the antiderivative, remember that 2 is just going to be along for the ride. So that constant multiple of 2, or the constant factor of 2, is just there. And then for the power of x, I need to add 1 to the power of x. So if I take -1/2 and add 1, I would get a +1/2. And then I need to divide by the new power, and the new power is a 1/2. So that's what I would get, and we should evaluate this from 4 to 25. And in this particular case, it might be nice to clean things up a little bit. Remember that when we divide by a fraction, that's the same thing as multiplying by its reciprocal. So dividing by a 1/2 is the same thing as multiplying by 2. So this would be a 4 times x to the 1/2, and x to the 1/2 is the square root of x. So this is a 4 root x evaluated from 4 to 25. Remember, you plug in the upper bound first, so this is a 4 root 25 minus a 4 root 4 when we plug in the lower bound, and that would be a 4 times 5, which is 20, minus a 4 times 2, which is 8. So we end up getting 12 as our final answer. Okay. So I think I'm actually going to call this video right now, because the next set of examples involve some u substitutions. So I'll break off these simpler ones, and we'll start with the u substitutions in